So today we have our first invited speaker, so Gilles Barthe, who is a research professor at IMDEA Institute, and his research is mainly about verification of cryptographic constructions, and he will talk about formal verification of side-channel attacks. Gilles.
Okay, thanks a lot. Good afternoon, and thanks very much for the invitation. I'm very good at bumping into stuff, so maybe I will just do this here. Okay, so what I will be presenting today is actually part of a much broader line of work, which is about trying to use formal verification and programming language techniques for cryptography. But what I will be presenting specifically today is about the application of these techniques to side channels. Okay, so this is a line of work which is kind of very practically motivated, because if you just look around, lots of crypto algorithms which have very good provable security proofs. Actually, when you start looking at the implementation, this is a big disaster. And there are multiple reasons why something which is actually provably secure ends up being implemented or turns into a very insecure implementation. So some of these issues have to do with a kind of legacy or implementation bugs, but also one of the main problem is really the problem of side channel, which has been discussed before this morning. And so we will be trying in this talk to focus on side channels, okay? So I'm not claiming that the other points are not important. In particular, trying to deal with implementation bug is something which is both very important and kind of amenable to the same kind of techniques as what I will be presenting. But for now, most of the work which my group of collaborators has been involved is mostly around side channels. Okay, and so why would we care about formal verification of side channels at all? Well, it turns out that if you actually look at these people who develop crypto implementation, not all of them, but most of them are actually pretty good and knowledgeable people, but they kind of still get it wrong. And they get it wrong for a reason. This is actually very hard to actually ensure whatever kind of side channels you're going to try to protect against, that you're kind of following some kind of design pattern which is going to make yourself somewhat protected against side channel. And so one very naive or simple-minded or obvious, whatever you want to call it, approach to deal with side channel is just by trying to carry some kind of empirical evaluation. This is something which is useful, but it's kind of insufficient, especially if you are at the design stage where you want to actually ensure that your implementation are as good as they can get. And also there is a whole part of crypto called leakage resilient crypto, which tries to address the problem of side channel, but it's from, at least from my point of view, a rather theoretical perspective, and it's not so easy to actually match the guarantees that are delivered by a leakage resilient crypto to what actually happens in practice. So what we would like to achieve in this work is actually obtaining formal guarantees on real implementation. So we want to look at the real code, and we want to have mathematical theorems about the fact that these implementation are secure against side channel. And if at all possible, we would like as well that these guarantees are fully automated, which means we're going to have a program which is going to take as input an implementation and is going to give a yes/no answer whether the program is going to be secure against side channel. And so in this talk, I will be talking about two different kind of side channels, which both have been discussed this morning. One is timing attacks, especially cache-based timing attacks, which have been quite devastating in the past and still are. And the other one, which is more specialized for implementation on small devices, is differential power analysis. And so there are kind of two different threads of research, but they have some commonalities. So the first commonality is like they're going to use this programming language and program verification techniques. So really we're going to use the same set of tools to attack this problem. They also have in common the way we go about modeling side channels, which I will actually explain in the next slide. And there are also some interesting interactions with provable security. So as I said, the focus of my talk is not provable security, but in both of these settings there are some kind of interesting interplay between provable security and side channel verification, and I'll try to say a bit more about this in each of the cases. So one of the things which might be actually confusing when you try to reason about side channel is like you move away from, so if you're a cryptographer, or maybe it's a bit different if you're a programming language person, but since you move away from the kind of abstract world of provable security, and you decide that you will consider reasoning about implementation, you know, just at the first thought you might need to think, or you might think like, okay, this is fine, but in order to do this, I really need to go very deep down into modeling hardware. I really need to be able to give models which like kind of capture to the last detail how platforms behave. And there is a very bad news, which is that people in programming language have spent a lot of time trying to give reasonably precise models of execution platform, and you know, you cannot go as far as giving a completely precise model. I mean, just to give one example, there was a group in Germany who spent a lot of time trying to kind of predict, well actually I'm talking about this group in Germany, but there are many groups who spend time trying to predict the execution time of program on a specific platform, and after many years of efforts, they were very happy because they could kind of predict the execution time with an accuracy which I don't remember, was maybe 10 or 15%. And this is actually something which they achieved many years ago and might not be possible anymore today, because the kind of execution platform are much more complex and more difficult to predict. So the bottom line is like, you should give up on the idea of having a completely precise model of hardware. This is actually not possible. And furthermore, I don't even think that this is desirable. And there are several reasons for this. One is like, you know, if you give one model for one platform, I mean, you will have to repeat this for as many platforms as you want to consider, and which is a kind of a lot of work. And on top of this, if you build verification techniques on top of overly precise model, when you will try to use your results, they will only be valid for one particular platform. So this is kind of a huge duplication of effort, and this is not really the way to go. And so I think the right way, or the right attitude to tackle this problem, is to try to stick to the philosophy of provable security, and trying to come up with models which are kind of achieve a reasonable trade-off between kind of being tractable and realistic. And so there's a kind of, this is very important to choose the right level of abstraction, because you know, if your model is overly simplified, you might miss some attacks. And if your model is too complex, you might not be able to do the verification. So you really have to choose the right level of abstraction. And so this is something very important, and in particular, you don't have to go in anything which I will present deep down into modeling the hardware. And then of course there is a standard warning when you use kind of constructed models. It's like there will be attacks that go out of your adversary model. So we've been looking at properties like cache timing attacks, and we have tools, and our tools might actually say, oh, this implementation is secure, but you know, actually we do the proof in a specific model, and it turns out that if you really look at the implementation, it will be possible to break it. I mean, I think this is still completely acceptable, and so I will try to say a few more words about this when I talk about these cache attacks. But this is something to keep in mind. I think, you know, this is a point which I would like to emphasize. You have to accept that even if you go lower down in the kind of details of implementation, you will only have guarantees which are relative to your adversary model, and this is fine. I don't think there is any other way forward. And the other thing which I think is kind of important is, so in particular for myself, I don't think I'm well, I don't consider myself a cryptographer. I don't consider myself an expert in kind of low-level execution platforms. So I feel very comfortable when I do this kind of work if I can actually pick a model which has been proposed by somebody else who has a better understanding of the problem involved. And I just take the model and I build verification tools on top of this. And I think there are kind of two advantages in trying to adopt this view. So first of all, if you rely on models which have been kind of mentally conceived, maybe not precisely formulated conceived by practitioners, I guess there's a good chance that they're going to be tractable, because you know, people try to use these models informally to guide their implementation. So I mean, that means that somehow they should be able to do the gymnastics to reason about whether an implementation is secure or not in their model. So this is some kind of informal guarantee of tractability. And also this is something which I mean, maybe looks obvious, but I would like to insist, because it turns out it's not always completely obvious in practice. So you always hear it's quite bad to roll your own crypto, but I think it's kind of equally bad to roll your own model of side channel, because you know, there's a lot of risk you're going to come up with a model which is either too weak or not meaningful. So I really think that using a model which is kind of developed by practitioner is some kind of big added value to the work. And of course, these models, in the ideal world, you would be able to kind of validate them formally. And at least for one example, I will show how it can be done. Okay, so in the first part of the talk, I will be talking about cache-based timing attacks. And so cache-based timing attacks are a very long history, so I could fill slides and slides of instances of such attacks. I mean, things are really pretty bad. There are lots of examples of implementations which are broken by such attacks, and such attacks in particular are a big problem because they can be executed remotely. And so the proposal which was put forward I guess by Dan Bernstein and a number of other people, to kind of minimize the attack surface against Cashbased timing attack, is to follow a discipline called constant time cryptography. And constant time cryptography has essentially two main rules. This is not the whole story, but the main rules are that the control flow should not depend on secret, so you should not have conditional or statements which branch on secret. So over here I use H as high, which in the programming language world stands for secret. So you don't want to branch on secret. That's rule number one. And so this rule actually is reflected in a weaker form of constant time security called the program counter model, which was proposed by Molnar and Wagner and some other people around, I guess, 2004 and 2005. And the second rule is that memory accesses should not depend on secret. So even if you have a public array, you should not access the array with a secret index. And so this is a problem in crypto, for example, if you use this lookup table. But I mean, it turns out that it is still possible to build efficient implementation adopting this constant time crypto, and that it is kind of considered as some kind of best practice against cache attacks. In the following sense, I mean, if you have an implementation which is obviously not constant time, there is a good chance that it can be broken. So this is actually the kind of standards that people try to, or most people try to follow when they implement their crypto. Of course, the model is constructed and it's no panacea. So it's fairly easy to see that there are attacks which are not captured by this kind of model. So in particular, there are some operations like divisions and many other where the execution times actually depends on the value of the operand, and this is not captured by the model. Still, I would like to argue that verifying that implementation or constant time is something which is valuable, and it saves you from a lot of, let's say, most obvious attacks. And this is not so easy to achieve. So, what is interesting about constant time is that it can actually be captured at the level, so it can be captured as a property of program, and it actually corresponds to a standard information flow property. So in programming language, when you try to reason about the security of a program, we have something called a semantics that describes the behavior of the program, and we can actually instrument the semantics so that it actually captures the behavior of the program and what the adversary can see in a kind of model where the adversary has access to side channel, and then you can express security within the semantics. And this is essentially what you can actually do with constant time security. You can actually say that a leakage does not depend on secret. Okay, so we have transitions which goes from state to state. This is a kind of iterated to give a semantics for executing full programs, and so the outcome of a full program will be a result plus a leakage, and you want to show that this leakage does not depend on secret. And so this is very useful because we're going to be able to use a programming language techniques to verify this. But one thing which I like very much about constant time security, and I think it has not been emphasized enough, is that it also has a very nice meaning if you look at much lower level, system level security. And so what we proved a few years ago with some colleagues is like, if you have a constant time program and you execute it in a virtualization platform where you have an adversary running in another partition, even if the adversary has some control over the cache and some control over the scheduler, it will still not be able to infer secrets from leakage. And this is actually valid under all realistic replacement policies. So this is a kind of a very nice result, which we actually formalized in proof assistance, so called COC, which we actually use to give a formal model of what it means to be a virtualization platform, how it works, what is the behavior, what it means to be a program. So we did it for x86 and to execute and so on, and we could come up with such a proof. And the proof is actually given in some idealized model of virtualization. So we have no branch prediction and no interrupt. And when I was mentioning earlier on in the talk that we don't really need to go deep down into the kind of details of the hardware platform. So of course we have some details which are present here. So for example, we have this page table, we have this cache, we have this TLB and so on. But we don't need to go very deep down, for example, in the formalization of page table and so on. So it's still possible to remain at a reasonable level of abstraction. And so this is actually something which is very comfortable, because we have at the same time this language level notion, which we're going to use for verification, and we have guarantees at system level. And this is kind of the ideal situation. What would be interesting to figure out is whether it can be extended to more realistic models. So could you try to do something similar with branch prediction and interrupt, because we know that these are kind of problematic kind of features. So it would be interesting to know what can be done in this setting. And also, can we do something similar for other notions? So one of the natural things one could try to do, and we actually did try, is to understand whether you can actually do something similar for quantitative notion of leakage. So instead of saying that you don't like secrets are not leaked, you could try to quantify how much of the secret is leaked. And the problem is like when we try to come up with such a result for quantitative notions of leakage, we have completely unrealistic assumptions. So that's not so clear, at least for us, about how can we extend this, let's say, to a quantitative setting. Okay, so we now have a clear target for verification, which is this language level. So how are we going to do it? Well, we have two approaches. One is, they are actually kind of very similar, and they are both relying on the fact that we are modeling this notion as an information flow policy. So when you want to say that the leakage does not depend on secret, what you are going to do is like you're going to consider two executions, and you assume that your secret are inputs to the program. So you're just going to say, okay, my inputs of the program, they correspond on the non-secret part, but the secret part can be arbitrary. And I'm going to run the program twice, and so I'm going to obtain the leakage, and I'm just going to compare these two leakages, and I require them to be equal. And if this property holds, that means that the leakage actually does not depend on the secret inputs. Okay? So this is how people view leakage in the information flow setting. And so when you want to reason about these two executions, you actually have two ways to go. Either you're going to take one program that is going to emulate the behavior of two executions, and this is what this product program is about, or you're going to develop a method to reason about two executions of a program at the same time. Okay, so the product construction, I just give one case here, which is the case for conditional, but you can imagine there's a similar case for, let's say, accessing an array, and then there are kind of trivial cases for the rest. So the way it's going to work, you have an if-then else statement, and you want to build a program which is going to simulate two execution of the if-then else on different inputs. And what you want is you want to achieve constant time. So in particular, it means that the control flow should not depend on secret. So that means like these two executions, they should actually follow the same control flow. Okay? So here you have this E, and what you're going to do is actually the basic idea is like you're going to make two copies of the program. Okay, so I type one copy with 1, I type the other copy with 2. You're going to run them in lockstep. So they're like you do one execution, one instruction of the program, another instruction of the program. And when you reach a branching point, you want them to enter into the same branch. So this is what is going on here. You're actually requesting that the value of the branch on the left is equal to the value on the branch on the right. And then you say, okay, if the value coincide that are true, then I do the two executions corresponding to S. If the value are false, I do the two execution corresponding to S prime. Okay, and so for the so in this way, you actually have a program that emulates the behavior of the two programs, except if the two programs have different control flow. If the control flow differs, this assert statement is going to return an error. So you know that if you have no error, the two programs have the same control flow. And this is what the verification is saying here. I have to start with two memories that coincide on the non-secret part, and I want that when I execute the program on the disjoint union of the memories, I don't get any error. That means that I don't reach an assert statement which is false. And what is nice with this notion of product program is like you start from two programs, you build a single program, and then you can feed this single program to a standard safety checker. And if this standard safety checker is telling you fine, then you know that you will be constant time. So this is something which is sound, which means you're going to catch all insecure program. It's relatively complete, which means that you know, if your safety checker were complete, then all secure programs will be accepted. You can use off-the-shelf tools, so we have an implementation for the LLVM, and we used it for many examples. So you can do really a lot of things with this. There is this other approach, which is based on instrumented program, and this other approach has some other flavor. You are going to take a program, and you're going to actually extend this program, so what we call instrument, with instruction that compute the leakage. So for example, here, when you branch, you know, right after the branch, you will extend the leakage by saying, oh, I went to the true branch, or I went to the false branch. So in the end, when you execute the program, as I said, you will have a result and the leakage. And what you want to show is like if you start with two memories which are equal, then you get same leakage. And this is actually an approach which is slightly more flexible. So in particular, they allow you to talk about constant time with public output, which is some kind of relaxation of the standard notion of constant time, where you know that the outputs are public, because if the outputs are public, whatever control flow you follow, which you could anyway infer from the public output, is kind of benign. So you can deal with this in this setting, and also it's compatible with EasyCrypt, which is the tool which we are developing for formal verification of provable security proofs. Okay, so we have tools for this. We have applied them to a lot of libraries, and the tool is performing very well. Now, one of the things that bugged us for a long time with this tool is like we were doing it at LLVM level, and so it's kind of a not so obvious question, at least to us. What does it mean like you verify your software-based countermeasure at one level, and then you actually do further compilation passes, and you're going to run the program. So it can actually be the case that you know, your compiler is going to break your countermeasure. It's actually pretty often the case that you know, if you try to kind of impose some countermeasure at source level, your compiler is going to ruin it. Now, what we actually realized this year is like for most program optimization, you can actually prove that the software-based countermeasure are preserved, which means like if you start with a constant time implementation, your compiler will actually return a constant time implementation. So as a word of warning, I'm not talking here about trying to understand what's going on, let's say, with GCC or CLang, because already understanding what they do without even caring what they do with side channel is kind of a big mess. But we're looking at a family of compilers which are called verified compiler, which are written with formal verification in mind. And for such compiler, they have a very clear description of their behavior. That code is not so messy, and you can do proofs about them, and this is actually what we did. And so what is interesting about it is like existing notions for doing compiler verification can actually not be used for the purpose of proving preservation of constant time. And it should not be so surprising, because when I described the constant time, I said it's a non-interference policy, and it talks about 2 executions. Actually, most work on formal verification reasons about single execution of programs. So what we had to do was to kind of generalize existing work for compiler verification in order to talk about side channel. So if you look about the way people do their program verification, normally, you know, you have a relationship between source and target program, and you actually show that if you do one step of execution at source level, you will actually have a matching execution step at target level. So, you know, if you start from A, and A is related to alpha, and you end up in B, then there exists a beta which is related to alpha, such that alpha executes to beta. So I'm talking here about deterministic programming languages, which make life a bit simpler, and I'm also talking about a very specific kind of a compilation path where one step of execution at source level is translated as one step of execution at assembly level. This is just for the purpose of illustration. We have a kind of other settings which actually corresponds to compilation passes where one step here is translated to an arbitrary number of steps here. I will say a bit more about this here. So here we actually do something similar, but because we're interested about 2 execution, we are not going to deal with a square, but rather with a cube. So we start with 2 executions, for which we want to establish a relationship. And we see that now on top of, like contrary to here, our execution are kind of labeled, and this label is the leakage. And so what you want to say is like, oh, I have these 2 executions here. I know they will be related to source execution. So if we assume that the source execution have the same leakage, I want to show that the target execution also have the same leakage, and moreover, like the states are being related. And if you can actually show this, and you know that your source execution is already constant time, then you know that the target execution is constant time. Okay, so if you're actually able to prove that your compiler satisfies this property, and you can prove individually or separately that your source program is constant time, then you know that your target program is constant time without having to do any further reasoning about it. And so that works very well. As I mentioned, if you really want to do something realistic, you need a kind of some variants of this where you just don't only have this lockstep stuff, but you have the one to several and one to any variance. One thing which is quite important is like when you do a compiler verification, you're like in this setting, you don't really care about the one to several and the one to any, with how many steps you're going to need here. Here, in order to reason about the leakage and say they are equivalent, you have to know that the number of steps which is going to be required to do like the low-level execution that match the high-level execution has to be kind of predictable and fixed. So you have to know this in your proof, but this is fine because this is actually something which you're always able to infer from knowing the instruction here. Okay, and so we have proved that it works for most optimization, like like standard data flow propagation. One of the stuff which Bug does for a long time is like when you do some variable spilling, you know, we were not completely sure whether like going to write in memory and so on was going to break constant time, but it actually turns out it does not. We have some kind of standard transformation that puts stuff in 3 address code, like this expression flattening, moving stuff out of loops, which is also, out of loops and conditional code motion, which is kind of instruction scheduling, reordering the code and so on. So we could prove in the setting of a toy language that all of this preserves constant time, but of course, I mean, there are kind of some bad optimization for which it doesn't work. So this is actually quite nice because in the end it tells you that you know, you can do your verification at a reasonable level of abstraction, and then you don't have to care anymore as long as you've done the right proofs on your compiler. Now, so much for verifying constant time. I want to say a few words about how it goes in the broader context. So right now, maybe a bit simplistically, but just to give you a very high level and very fast flavor, you could say like there are 2 kind of big trends in building crypto libraries. So there's the idea of high-speed crypto, where you really, so let's say this is the kind of implementation you will write in a language like Chasm or Perl-Asm or whatever, and you really try to go for really fast code. You try to take advantage of low-level optimization, and in general this comes without formal guarantees. And on the other hand, there's a more recent line of work which people often call Highassurance crypto, where you actually formally verify your implementation. In general, you mostly verify functional verification. Occasionally, people verify side channel, including using the tool CTverif, which is based on the techniques which I presented in the previous slides. And sometimes, but this is mostly us, people actually do provable security proof. Now, this is actually fine, but most of these programs are actually written in C-like language, and the compiler is in the trusted computing base, which is normally quite a big assumption to trust your compiler. Like, not only you trust it's correct, but also you trust that it preserves security. And the code is reasonably efficient, but it does not match high-speed crypto. So what I claim is like we can actually make the best of the both worlds and achieve a fast and verified assembly implementation. So a couple of years ago we had a preliminary case study for a component of TLS where we actually used a number of tools. We did the provable security proof using EasyCrypt, which is, as I said before, the tool which we have developed for verifying provable security. We actually showed that the EasyCrypt code corresponded with a C implementation. Then we used a verified compiler to obtain assembly, which was provably functionally equivalent to the source level implementation, and by transitivity equivalent to the specification in EasyCrypt. And then we used our tools to prove the compile code is constant time. So this is kind of some of the way, but still, you know, we don't really have this handwritten, low-level optimization and so on. So there's a way to be a bit more ambitious, and so what we can hope is like have a kind of separation of constants, which actually really delivers the best of both worlds. So you're just going to prove, using a tool like ACNS, that your algorithm is provably secure. You're going to write a reference implementation and show it's safe and functionally correct and equivalent to the algorithm. And then you're going to write an optimized implementation and show it's functionally equivalent to the reference optimization and itself being safe. So safety, I'm not going to say too much about it, but it essentially kind of prerequisite for everything which I'm saying to have a meaning. That means the programs have a meaning and so on. And then you have to show that the optimized implementation is leakage-free. And actually, if you have all of this, you can actually show that if an adversary with side channel access can break the optimized implementation, then there is a standard adversary that can break the algorithm. And this is normally what you have proof is not possible under some assumption in ACNS. So this is not possible. Again, modular assumption. And so we are developing a framework called Jasmine, which is actually meant to kind of achieve this goal. So it's like very shortly and incorrectly, you could say it's a chasm, but with the semantics and correctness proofs. It's a kind of a programmer and verification friendly language. So we actually try to propose features that make programming in this language look familiar. So in particular, we have names, we have loops, we have function. But because you want to achieve a high speed, we also have a support for low-level instruction and intrinsics, so that if you really want to write a very fast code, you should be able to do so. At the level of efficiency, it's actually competitive with a Chasm and sometimes faster. I don't think we have too much merit on this because possibly, you know, we haven't built such extensive library, and then we spend more time than other people. So by spending more time, we manage to find more optimization, but it's not necessarily a sign that our language is better, it's just we spend more time. But at least it's good to know we are as fast. That's the good thing. And then our compiler is predictable, because really the idea is like the programmer knows how to do things, and he wants to be in control. It's formally verified, so we know that it preserves the meaning of programs. We have automated proofs of safety and constant time. And so this actually goes as far as what has been done for the MECBC example. If you want to go further, you actually need to have this very good tool for proving equivalence between reference and optimized implementation. And the technique which we are pursuing here is a code-based equivalence checking. So the idea is like we're going to use this game hopping strategy that people use for provable security, because it's actually much easier to understand, much easier to automate, so for exactly the same reason. But we're not going to use it for provable security, we're just going to use it for proving that the two programs have the same behavior. And it actually seems to work pretty nicely in practice. And then one of the goals would be to apply the techniques that we've been developing for preservation of constant time to this compiler. We have not done it because there are essentially two ways to describe the semantics of programming language, and one is compatible with what we have been doing for preservation of constant time, and the other is not compatible. And for now, what is formally verified in the code proof assistant is actually using this other style of semantics. So for those who know, we are using a big step semantics, and for preservation of constant time we need a small step semantics. So, I mean, there's no difficulty in switching from one to the other, and this has been done, for example, in the past for verifying compilers like CompSert. It's just a pain, and we'll have to go through it at some point, but we have not yet started. Okay, now I'll go very quickly over the other thing, which is power analysis. So there were already some talk on differential power analysis this morning, so I'll go very quickly over the motivation. And again, the idea, we are going to look at this masked implementation, so you are kind of using additive secret sharing for values, and you try to develop implementations that operate on this, and this is messy, this is easy to get it wrong. And so there is this notion of proving security, which is proposed in the setting of the ISW model, which is essentially saying that the program is secure at order T, if and only if, when you look at an arbitrary set of observation of size smaller than T, it can be simulated with at most T share from each input, which kind of more plainly translates into the joint distribution for a set of observation of size smaller than T is independent from secret. And again, this is something which relates to information flow, and because independence from secret is non-interference, and it gives us an opportunity to leverage programming language techniques. So about the security model here, we don't really have a model of a platform and the proof that the ISW model is meaningful, but there is this equivalence with the noisy leakage model which people have established, notably at Eurocrypt 2014. Okay? So there's still a number of, it's an interesting point to note that this is a non-interference, but there's a number of challenges. One is that you have to show independence from secret, so you have to know how to do probabilistic non-interference, but mostly there's also a problem of explosion, because you have to do the verification for all set of observations, so this completely blows up. And then there's the problem of composition, like this approach works for small gadgets, and how you deal with composition is a kind of an issue. And then the other question is like, you know, these gadgets, they are not so simple, so it's sometimes not so easy to see whether you can do stuff which is kind of more optimal. So can you kind of improve in randomness complexity, or can you try to make implementations that are easier to parallelize and so on? So there's a number of issues which actually are kind of interesting from the point of view of formal verification. So checking independence from a secret is actually something which can be done, as I said, using ideas from probabilistic non-interference. So we have a very simple set of rules, and essentially rule one is like, yeah, I'm done. You know, like if I have to look at the set of observation and like really when I compute the expression that correspond to this observation, I get an expression that does not depend on the secret, then I'm fine. Then the next step is actually when you don't have such a case, but you have syntactic dependency. What you can do is you can apply optimistic sampling. I was presented this morning by Jean-Sébastien, and you kind of try to repeatedly apply optimistic sampling until you fall into the first case. And it actually works most of the time in practice, except that very seldom you get stuck. And then if you get stuck, we have a rule 3, which we don't often mention because it's not always needed. As I said, we use it very seldom. But essentially, if we get stuck, we cannot apply rule 1 and we cannot apply rule 2 any longer, we have some decision procedure which actually helps you decide whether you're independent or secret. The problem of this decision procedure is like it's expensive, so we try to use it as little as possible. Okay, so This is kind of the approach, and initially it's only set up for dealing with a single set of observation, but actually this particular algorithm has a number of benefits, so it's actually very easy to automate, and it's very fast. But on top of this, it also extends to large sets. So one of the issues is like when you verify at higher order, you have to verify for all sets. Well, we're going all sets of size smaller than t. And so what we are going here to do is something slightly different. We're going to try to verify for much bigger sets, but a smaller number of them. So like theoretically, it doesn't make any difference. Like this is, both of them are kind of untractable, but in practice, this approach seems to work very well. So what happens in kind of the background is like when we apply optimistic sampling, we kind of building a bijection between the randoms of the two executions. And when we are done, we have a bijection which is built, and then we can use this bijection to test equivalence between large sets. So I know what I'm saying is kind of a bit vague, but I'm trying to convey the idea why it actually works a bit better. Because like the difficult part is building the bijection and then like checking for how big sets, as big a set as possible, whether the bijection actually works is something which is possible. And so we're taking advantage of this, and it actually works well on individual gadget up to small order. So just to give you one example with this approach, and it's not a gadget, but I guess at other two, we can do, for example, 4 rounds of AES fairly fast. Okay? There's a further problem with composition, and so essentially the problem is like when you're composing gadgets that are secure in the ISW which are probably secure unless you put sufficient refreshing gadget and the right type of refreshing gadget, you won't have something which is secure. And the basic idea is like if you use the simulation-based definition to try to understand this, is like you have this composed gadget here, and you are up to t observation, and you decide to place your observation in different places. And then when you're using the simulation, you're going to take this T3 observation and you're going to push them on A2, so you get T2 plus T3 observation. You're going to push them on A1, you get T1 plus T3. Then you apply the simulator from A2 to A1, so you're going to get here T1 plus T2 plus T3 plus T3, because you get one T3 from here and one T3 by going through here. And so when you apply one more, you're going to get T0 plus T1 plus T2 plus 2T3, and you're kind of violating the constraints, so you cannot conclude security. And this actually gave rise to a lot of issues in reasoning about full implementation, the security of full masked implementation. And so what we came up with the notion of shell non-interference, which has a slightly different way of counting, and actually he's also satisfied by a lot of gadgets. So kind of I'm slightly contradicting myself, because we came up with our own notion of security in this particular case. But the good thing was that it's actually satisfied by many gadgets from the literature. So that was kind of useful to realize we're not working on the empty set. And with this, so essentially we're distinguishing between internal variable and output variable, and we're requiring that the number of share you need for simulating actually only depends on the number of internal variable. And when you actually repeat the experience here, you actually show that you can actually see that things go fine. Okay, and so using this, we actually, so maybe I don't go into the details of this, but for those of you who are going to attend CHESS, there will actually be a complete tutorial on this masked implementation and this technique, so maybe you will be interested in attending. And so we have two tools. One is really for verifying individual gadget, and we are verifying lots of properties. We've recently extending our tool to deal with glitches. So we're able to do the same kind of example as the paper by Bloom and Manga and some of the people at Eurocrypt this year, but we go way faster. We can also synthesize gadgets, so actually we have a program that is coming up with new gadgets that achieve security and have a better kind of property in terms of randomness complexity. And we've got another tool which is called mask-comp that takes a C-like implementation and returns a masked C-like implementation, and it's kind of delivering reasonably efficient code, and it's delivering code at arbitrary order. So I have some statistics here, but I'll skip. So since I'm running late, I will just go very quickly. We recently extended, we recently considered how to mask post-quantum implementation. And what is interesting with post-quantum implementation is like they have, in particular, non-trivial control flow. They do this kind of rejection sampling. And so if you really want to have an efficient implementation, you have to accept that you will leak the control flow of your program. And that means that two things: you will have to consider a notion of non-interference which is weaker, which is kind of non-interference modulo output, but this notion is actually not very meaningful on its own. So if you want to state security of your mask implementation, you really have to define a notion of unforgeability under adversarially chosen leakage, which is actually something specific for masking, but that's the only way to make sense of what you prove. But in order to establish this, you actually need to go back to the security proof of the original scheme and actually prove that it achieves security by leaking as well the randomness, or the control flow itself. So this is kind of some interesting interaction between side channel and provable security. And so just to conclude, we have some great tools. Well, okay, maybe I shouldn't conclude so quickly because I have a stupid conclusion, otherwise we're great and so on. But we have kind of tools for analyzing side channels. They are compatible with provable security, and we can, or we hope that we will soon have the ability for crypto primitives, I'm not talking about protocol, to have high-speed, fully verified implementation. And we do a lot of other work, which you're welcome to go and check on my co-author's webpage, because my webpage is a disaster, where we use this kind of programming language techniques for a lot of other things. Thanks for your attention.
Any questions for you?
So what are the main open problems in this area? Is it to obtain better models, to obtain a better modelization of the hardware, or to have more comprehensive models, or to be able to have efficient verification of the security in a given model?
So you mean on the cache-based, for example?
Yeah.
Verification is actually very efficient. We have been using so we built on top of a tool which was developed by somebody who's now at SRI, and so because we can piggyback on standard safety verification, which is something where formal method is very good, we can verify code very quickly. I think we verified 70,000 lines very fast. I think what would be interesting is more, I mean, this is more trying to understand how you can accommodate, reasoning about this speculative execution and interrupt things that people know are kind of problematic. And so if you could come up with this language level versus system level security, there's lots of papers that are actually trying to understand how to achieve system level security in presence of speculative execution. So if you could lift this back to language level, and then I would expect that you would be able to verify efficiently. So I guess a lot of the work right now is like motivated by this spectrum meltdown, where people really try to come up with models which re-establish kind of non-interference properties. There are probably many works like this, but there is a recent paper by, I think it's Srini Devadas at MIT, about trying to re-establish non-interference property in presence of speculative execution. I'm sure lots of people are looking at this. So that would be one of the main challenges. And the other crazy stuff, if you really want, like, what would be very hard is like, take these acoustic side channels and then try to formally verify that you know, you're protected. I think that's crazy. I do not recommend anybody to work on such a topic, but and there are some very hard problems. The problem is whether the payoff is good.
Any more questions? If not, let's thank you again.